Okay, so we'll continue on here, and all right. So we said if it's linear, then we can do it. Okay, so then for linear relationships, there are kind of aspects of a relationship that we want to kind of explain, and that it would be so we have positive relationships. And we have negative relationships. Okay, and these are just kind of like overall. So positive relationships, the overall trend is large values of x go with large values of y. Okay, and then the overall trend is that also that small values of x go with small y. Okay, and then for a negative relationship, again, the general trend is that here we have large x goes with small y, and you have small x goes with large y. Okay, and so a positive relationship, again talking overall, looks something like this. You have something kind of in this direction where you've got, here you have small x, maybe small x and small y. And so you've got the relationship here, and then over here you've got large x and large y. And overall over here you're going to have a trend like this. Okay, so this over here is large x but goes with small y, and small x goes with large y. So the overall trend, something kind of, the overall relationship is something like that. Okay, so you got positive and you got negative relationships. Okay, and then we can talk about whether there is a strong, weak, or strong relationship. Okay, so in a strong relationship, there's little scatter. Little scatter around quote unquote the line. So I mean the line is kind of just this imaginary trend line, but in a strong relationship there's going to be little scatter around the line, and then in a weak relationship there will be much more scatter. Around the quote trend line. So again, and I put line in quotes because the line isn't actually part of your data, it's just something that we can add to kind of explain the relationship. Okay, and so we have a summary statistic called the correlation coefficient. Okay. It's often just called correlation for short, okay? And the symbol is R, okay? R for like a relationship. Okay, and I'm going to give you interpretations of R. Now, R is just the results of a formula, okay? And so even if the data is a nonlinear relationship, you can still calculate a value of R, okay? So even when X and Y do not have a linear relationship, you can get a value of R. Okay? But the interpretations that I'll provide here only make sense if the relationship is linear. Okay? Okay, and so so basically the sign of R is the direction of the relationship. So positive R means you've got a positive relationship. Negative R means you've got a negative relationship. Okay, so R greater than 0 means kind of something like that. R less than 0 means like that. What do you think R equals to 0 would mean? Yes, kind of R0 would be, it would be flat. Something like that, okay?
Does it mean there's no relationship?
Yeah, no relationship. R equals 0 means no linear relationship, I should say. Okay, neither positive nor negative. Okay. Yeah, I mean, like it's flat, but it doesn't count as a relationship. There's just no relationship there. Okay, and then R can take on values between -1 and 1. So R is always between -1 and 1. So, and if R is close to 0, the strength is weak. And if R is far from 0, meaning close to 1 or close to -1, relationship is strong. The strength is high. Yes?
What's like a good cutoff point?
It all depends on the situation that you're dealing with. So with people, you would be excited if your R is like over 0.6. If you're dealing with robots, you would probably be very angry if your R is less than 0.9. Okay, so you know, or like with machines, you know, I think you would have a disastrous production process if your correlation is probably less than 0.97 or something like that. You just kind of means there's, like, if it's like how many, if you're trying to predict like how many pieces of product you can produce in a certain amount of time, like there should be a very, very strong linear relationship. I mean, I'm assuming kind of like this, a standard mechanical process thing, and if you've got, you know, less than 9795, it's probably, you know, your machine is not very reliable type of thing. So but then with people, or, you know, living beings, where things are much more complicated, it's you're gonna have values all over the place. Okay, and so you know, in the text, there's kind of some examples. So I'm gonna kind of do this. So these are supposed to be perfectly straight lines, all of them, okay? And okay, all of these will have r equal to what? +1. Okay, so the slope doesn't matter. It's just as long as there's a positive trend, okay, meaning large X goes with large Y, you're gonna have a positive thing. And because they're all, you know, in a perfectly straight line, there's no scatter around, you know, if we imagine some trend line to exist, okay, so there's, let me use a thin pencil here. Where's my, so because all of these, well, so this one, you know, so there's no scatter, they all are in a positive direction, you've got r equal to 1 there, okay? Whereas, you know, as soon as we introduce a little bit of scatter, then r is no longer. So something like this, where there's a little bit of scatter, this is probably going to be like r equal to 0.97 or something like that. What's going on here? And then as you introduce more and more scatter, the R value is going to go down. Yes?
So when the line is a flat line,
Uh-huh.
you said R equals 0, right?
Right.
But what if that flat line is a result of points that are completely, like, that fall within the line? Outliers?
No, it's different. So a flat line, okay, a flat line is a flat line, and here r is 0, okay? So if I have dots like this on a perfectly flat line, r is 0. So here this would be kind of like, I don't know, let's say, okay, so like in a cave, there's like stalagmites that grow, right? And it's like because water drips down, and it's like like the minerals in the water accumulate and harden. And so they grow at a steady rate, but it's a very, very, very slow rate, okay? And so here it could be like years passed and the length of the stalagmite, okay? And so it would be like many years have passed and it has grown 2 millimeters or something like that, okay? So you're gonna have a very low slope, okay? However, is there definitely a trend between the amount of time passed and the length of the stalagmite? Yes, and we might be able to predict very, very well how long the stalagmite is based on its length and things like that, and that's kind of how they date caves and stuff. And so, we have this very thing like this, okay? Over here where it's completely flat, this means there's just no relationship. This would be the same number appears over and over and over again. It would be like, is there a relationship between, I don't know, the year since, the year and how many days are in a week, okay? And there's no relationship because since we've invented the calendar with a 7-day week, the number of days in the week is 7, okay? So there's no relationship there. Whereas, other things, how tall is, I don't know, how whatever else, something, yeah.
So the equation to calculate R, if there is no change in Y according to X, it gives you an R of 0.
Yeah. We'll go through the calculation to calculate R, okay? But, so we get something like this, and then, and of course, anything in the negative direction. Yes, question?
What if you get like R is equal to 0.01? Is it like close enough to 0 that you say is basically no linear relationship?
Oh, R is 0.01?
Yeah, or like some very, very small.
Yeah, that happens too. So yeah, okay, so here, R would be something that, I don't know. I'm just making up these numbers. This is like about, okay, about negative 0.6, okay? Yeah, so we might have like a cloud of points that looks like this, okay? And I would draw this and I would say R is probably equal to 0. But if I plugged in all of these points into the computer, it would probably actually, maybe is close enough to R equals 0.0, but maybe the computer would tell me like, oh no, if you actually look at it, there's a tiny little negative trend and it's, R equal to negative 0.01 or something like that. So yeah, we would just say there's a very weak trend that it's not really even worth saying exists. But, well, this brings up a good, all of these are actually all related, all of these questions you've asked. So we'll talk about how to calculate R, and I think it'll give us kind of an understanding of how this works. And then just like all of these other tests, statistical tests that we've had, we will have a statistical test that basically answers the question, is this value of R significantly different from 0 or not, okay? So, whereas, before it was like, is the difference between x bar 1 and x bar 2, is that significantly different from 0, meaning that there's a difference in the population? We'll ask, in the data that I have, is the correlation that I observed, is that significantly different from 0 or not? Okay, so we will we'll approach that. Okay, so we have this, and then again, if I have something like this, okay, the idea with R here is that it would try to like it's like pretending that there's a straight line here or something, and then it would look at the kind of the scatter around this line, and then so it would like if we were to stick these points into the formula, it would probably spit out R is equal to 0.7 or something like that, okay? But this is not going to be useful to, the interpretation here is not going to be useful, okay? Because this relationship is not linear. Okay, so R does not really make sense. So R, you should really only use R for linear relationships, okay? Whereas something like, if we had data that looks like this, it would probably spit out R equal to 0 because it would try to fit something, it would try to probably fit something like this to the data, okay? So both of these are nonlinear relationships. Does not make sense to use R in these cases. Okay, so let's talk about calculating R. And for this, I will make up a silly data set, but I think illustrative of what we need to do. Okay, so we're going to say we're going to look at a few different dwellings. Okay, X will be the number of bedrooms in this, in said apartment or house, and Y will be the number of closets. Okay. And we want to know, is there a relationship between the number of bedrooms and the number of closets? Okay. And this is not really this is probably not a random sample, but we're gonna just pretend for the purposes of this we're gonna have this. Okay. Okay, so this is what I have, and so I'm going to graph this. Okay, so 2. All right, I hope this is good enough picture here. Okay. All right, and so the formula for R is this: 1 over n minus 1 times the sum of basically the z-score of x multiplied by the z-score of y. Okay, so what is a z-score? The distance. So z-score is our distance from the mean expressed in standard deviations. Okay. So so as far as this goes, it's n minus 1, and then the z-score for x is going to be the distance that x is from its mean, x minus x bar, the distance from the mean, but expressed in standard deviations. So we're going to divide by the standard deviations of x. Okay, and then same thing. So we're going to multiply this for y. So it's going to be y minus y bar divided by the standard deviation of y. So it's the distance from the mean in standard deviations for x, and the distance from the mean for y expressed in standard deviations. Okay, and then we're going to do this for all data points. So there's technically like a little subscript I here to indicate that we're going to do it for all data points, and then and we multiply them together. So the square root, or I'm sorry, the standard deviation of x and the standard deviation of y are going to be the same for all data points. Like this data point, if we ask what's the standard deviation of x, it's going to be the standard deviation of x. So we can actually factor those out. So this is going to become 1 over n minus 1 times, and we're going to factor out the standard deviation of x, the standard deviation of y, and now I just have x minus x bar times y minus y bar. Okay. All right, so we will use this, and we'll try to get the correlation of between x and y. Okay, so I got x here, I've got y here, and then I'm going to do x minus x bar, and then I'll do y minus y bar, and then I'll do kind of the product. So 1, 2, 3, 4, 2, 6, 4, 8. Okay, so the mean x bar, what is x bar? Yeah, 2.5. I add up these numbers, I get 10, I divide by 4, and I get 2.5. And y bar is 5, right? I add these ones up, I get 20, I divide by 4, and I get 5. Okay, so I'm going to kind of draw a line here at 2.5 to indicate the mean of x. I'm going to draw a line here at 5 to indicate the mean for y. So this is y bar, and this line represents x bar. Okay, and so what we see is that the value 1 is 1.5 lower than the mean. So this value here is 1.5 units lower than x bar. And for the y value, it is 3 units less than y bar. Okay, so 2 is half a unit less than x bar, and 6 is 1 unit above y bar. Yeah. Wait. Okay, and all right, so over here at 3, we are half a point above x, and we are 1 point below the mean. So I got 0.5 and -1. And then over here at 4, I am 1.5 above. 4 minus 2.5 is 1.5, and 8 minus 5, I am 3 above. Okay. Oh, it should be -3. You are absolutely correct. Okay. Okay, and so when I multiply these together, I get a positive 4.5. Negative 1.5 times -3 is positive 4.5. Here I get a negative 0.5. Here I also get a negative 0.5. And here I get a positive 4.5. Okay. And so I'm going to add all of these up now, and I get this value to be 8. Okay, and so our R value is going to be 1 over n minus 1 times 1 over the standard deviation of x times 1 over the standard deviation of y, and then all of this multiplied together and added up is now 8. Okay, and so you can do the calculation yourself, but I'm pretty sure I'm pretty sure the standard deviation of x is going to be 1.291, and then 1.291, and this one ends up being 2.582, okay, rounded off. Okay, standard deviation. So that's, do you guys remember how to take the standard deviation of x? It's, you just kind of plug it in, you know, as far as standard deviation goes, it's, you know, x, or I guess whatever it is, x minus x bar quantity squared distance from the mean average, something like this, right? Okay. So anyway, we do this. Okay, so now we have 1 over n minus 1. We have 4 data points, so we're going to have 1 over 3, times 1 over 1.291 times 1 over 2.582 times 8, and all of this comes out to be 0.8 R. So my correlation between these, the x and y variables for these 4 data points is R equal to 0.8. So there's a positive trend and maybe not a ton of scatter. Okay, that's what we have. And so if we, I think the kind of the key part here is this x minus x bar and y minus y bar, the product here. Okay, and so what we see is that this data point, it is below below x bar, and it's below y bar. Okay, and so in a positive relationship, we say small values of x go with small values of y, and large values of x go with large values of y. Okay, and so this point, because it's below the x and below the y, it's going to be negative and negative, and it's going to contribute a positive amount towards the correlation. Okay, so things in these direction, so which is kind of the overall positive, these contribute positive. To R, contribute positive values to R, right? And this one's above x and it's above y, so you're going to get positive 1.5 times positive 3. It's going to contribute a positive value. Okay, and over here, these things. Okay, so you know, we said the overall direction for positive, you know, goes from kind of the lower left to the upper right. The overall direction for the negative starts in the upper left and goes to the lower right. So we can see that these ones contribute to the negative. Or contribute minus negative values to R. Okay, and we can see that negative 0.5 times 1 gives me a negative 0.5, and this one also gives me a negative 0.5. So these contribute in the negative direction. And what we see is that kind of the amount contributed towards the positive outweighs the amount contributed in the negative direction. And so the overall correlation will be positive here. Is that good? Okay, and then so, you know, just kind of, so if I had the data points like this, what would our value be?
0.
Yeah, R here would be 0, okay? Because if I graphed kind of what x bar is, x bar would be right here, and then y bar would be right here, we would see the amount contributed in the positive direction. So this is positive, and this is going to contribute in the positive direction. We see that these all get canceled by the amount contributed in the negative direction. Okay. So they all cancel each other out. Okay, and you know, obviously it's not gonna, like, every data set won't be so nice and neat, but I hope it kind of makes sense as to how we are arriving at such a correlation value here. Okay. Okay, and then so let me just set this aside here. Okay, and then okay, so let's go back to this. And then so we kind of, so in this data set we said, okay, R ends up being equal to 0.8. Okay, and so the question now is this significantly different from 0? Okay, is R equal to 0.8 significantly different from 0? And what we mean by that is that we're going to set up a hypothesis test, okay? So does the fact that I have r equal to 0.8 indicate that in the population there is a positive, or that there is a non-zero correlation between x and y, okay? So is there, does our data, or do our data provide evidence that in the population the correlation between x and y is not zero, okay? And so we're going to conduct a hypothesis test here. All right, and so the null hypothesis is that the correlation between x and y in the population is 0. Okay. Symbolically, we would write that the correlation in the population is equal to 0, okay? And so the symbol we use for the correlation in the population is not r, because r is the correlation in our sample. It's the Greek analog to r, which is rho. And rho looks like a p, but it's not. Okay, this is rho, okay? And we would say rho is equal to 0, okay? Like in Russian, they still use rho, but it's and it looks like a P, but it's pronounced with the R sound, okay? So anyway, so we have this, all right? And so this is to indicate the correlation in the population. So I know we have the letter P that appears a lot in all of these things, and we have something that looks like a P, but it's not a P. And this is the rho, okay? So that would be the null hypothesis, and then the alternative would either be that the correlation is positive, or the correlation is not equal to 0, or the correlation is negative, or something like that, right? So, and then, so we have that, and then, you might have the alternative being rho is not equal to 0, or rho is less than 0, or rho is greater than 0, or whatever you might have, okay? Okay, and I'm gonna just kind of like wave my hands and say, to test this, we have this test statistic, and I'm not gonna try to explain where it came from, but we're just gonna say, hey, what do you know? The test statistic is going to be t equal to r times the square root of n minus 2 divided by 1 minus r squared. Okay. And then and you would look up in the t-table with degrees of freedom equal to, this time, n minus 2 degrees of freedom, okay? And the reason why we're doing, we have n minus 2 degrees of freedom is that because a line is defined by 2 points. So if you just had 2 points in your data set, they will always be in a perfectly straight line, okay? So we can only start to ask, are they, is the correlation significant when there's more than two data points, okay? All right, so let's try this out for our test, and we might ask the question, does our data provide evidence that the correlation between x and y is not 0, okay? So we've got, we have 4 data points. Our r is 0.8, okay? So our test statistic would be r times the square root of n minus 2 over 1 minus r squared, okay? And then our null and our alternative hypotheses, we can say rho is equal to 0, and we can just ask, maybe we'll say, is rho greater than 0? So we'd say, so this means there's no correlation between the number of bedrooms and how many closets you have. Okay, and then the alternative will be that there is a positive correlation. Okay. All right, so let's try this out. And so our test statistic will be 0.8 times the square root of 4 minus 2 divided by 1 minus r squared is 0.64. So I have 0.8 times the square root of 2 divided by 0.36. And what does this come out to be? I'm getting 1.886, something like that. Okay, so now we would look this up with look up in t-table with 2 degrees of freedom. Okay, so here we have a one-sided test. Oh, and what do you know? This is one of those rare times where our test statistic is exactly the value in the t-table. Okay, so so here we have our tail area exactly equal to 10%. All right, and because it's one directional, we won't double this, and so we will say our p-value is equal to 10%. Okay, so this is we have a directional alternative. I guess we should have done a directionality check, which we passed because our correlation is positive, right? Okay, so our p-value is 10%. All right, what does that mean? So, I mean, well, what do you think? Should we reject or not reject the null hypothesis?
Is there an alpha?
I don't know. Probably alpha 5%, and we would say don't reject, right? Okay, so if alpha is 5%, okay, we would not reject the null hypothesis. All right, so so what does this mean? So we're getting a p-value equal to 10%. So our p-value is equal to 10%. So what this means is that, you know, if the null hypothesis were true, so if there were no correlation between X and Y in the population, if there were no correlation between X and Y in the population, then the probability that 4 randomly selected points producing a correlation of 0.8 or something more positive just from random chance is about 10%. This happens about 10% of the time. Okay? So the probability that 4 random points produce an R of 0.1 or more is 10%. Okay, our p-value. Okay, or another way to think of this is that I could close my eyes and throw darts, 4 darts at a wall. Okay? And if I throw 4 darts at a wall, from random chance, it might appear that they're in a somewhat of a straight line. Okay? And we could actually, you know, if I threw darts at a wall where there were grid lines, we could calculate the quote correlation, or the correlation between the locations of those 4, you know, points where the darts landed. Okay? And it says about 10% of the time you would get a correlation of 0.8 or more, okay, just from throwing 4 darts at random at the wall.
So that's supposed to be 0.8.
I was just thinking.
Oh, yeah, I'm sorry.
Okay.
Produce an R of 0.8 or more. Yeah, I'm sorry. I'm getting, yeah, from random chance. Okay, 4 random points produce an R of 0.8 or more is 10%, yeah. So that, something like that could happen with quite a bit of frequency. Okay, so but you know, if you have, and part of the problem is that I only have four darts, right? So you know, with 4 darts it's easy to end up with just a pattern by chance. Okay, but if I had like 50 darts and then we calculated the correlation and then I'm getting an R of 0.8, then it would feel very suspicious that, you know, maybe I was trying to make kind of a pattern, a lined pattern or something like that, which for me would be quite impressive if I could pull that off. But so that's what we have here. Okay, does that make sense there? Okay, why don't we take a short break here, and then we'll come back and we'll talk about linear regression and how all of that works out.